All right, we're back as previously stated. Circuits have three parts: have batteries, continuous conductors that go from the positive terminal to the negative terminal of the battery, and then out to and then through a light bulb or some other device that converts energy. So you put energy into a circuit, and then you will get energy out. The rate at which energy is transformed or transferred is referred to as power, or electrical power in the case of charges moving. So power is defined as how much work is done per unit time, or how many joules are consumed or transformed every second. And if we look at the electrical definition of work, work as previously stated would be Q times delta V from our potential chapter. So QV will do it. And if we look at QV, this will carry units of coulombs times joules per coulomb. So Q are coulombs, charge is coulomb, and potential difference are joules per coulomb, or voltage. So we end up with units of joules. If we do QV divided by T, we get the powers work over time. Q over T is I. So electrical power can be computed by taking the product of the current, I, times the potential difference, V, voltage. If you increase the current, you'll increase the power output. If you increase the voltage, again, you'll increase the power output. You'll get more energy out every second. So another way to think about electrical power is the rate at which energy is transformed. If we have a pipe with water flowing, you can connect a generator to this, and the rate at which this spins is, the water wheel spins, is related to the electrical power. So the water at the top has GPE, gravitational potential energy. It gets transformed into KE. As the water falls, it loses gravitational potential energy. The wheel turns and the water falls, doing work. Electrical circuits are similar. As charge falls from a high potential to a low potential, from a high to a low, energy is transformed, and we can use this to run a light bulb, a motor, and so on. What is the unit of power? That's the question exactly. It's actually joules per second, which are watts. Can we rewrite electrical power using Ohm's law? Power is I times V, so here's the first equation. Given Ohm's law, I equals V over R. If we put in V over R where I was, we get power is V times V over R. So power is V squared over R. So let's just circle the many ways we can define it. The first one is I times V. The second one is V squared over R. And then the third one, again using power is I times V and V is I times R. So we'll get power is I times R, I squared R. So we end up having it our way. There are three different ways we can define electrical power. I'm going to write them quickly, and then we'll come back and paste this into memory for later use. Power is I times V, is I squared times R, is V squared over R. So I'm going to take and paste this into memory. Let's just highlight the whole thing. Copy it, whoops, and we'll pull that back out soon enough. Batteries are sources of energy or sources of power, and as previously stated, DC, AAA, AA all have a potential difference of 1.5 volts, and 9 volts have a difference of 9 volts. So in theory, the 9 volt could produce more energy every second because you'd have charge falling through a greater potential difference or being elevated, whichever you prefer. So here we go. We'll solve some problems out related to electrical power. A toy's electric motor has a resistance R of 17 ohms and a potential difference of 6 volts. So when you apply a potential difference across the resistor, charge will move and power is generated. So let's go ahead and paste our equations. From memory. There they are. So this will give us the relationship between power, current, voltage, and resistance. And if you look here, we're given voltage and resistance. So we could use the fact that, and I'll just underline, power is indeed equal to voltage squared over resistance. So I'll write P is V squared over R, and we can sub the numbers in. We get 6 volts squared divided by the resistance, 17 ohms. So it's going to be 36 over 17. Let's reveal the answer. We end up with 2.118 watts. That means about 2 joules of energy are converted every second. Not a lot of energy, really. Next, a toy's electric motor has a resistance of 6 ohms. And we have 7 volts applied to that. So again, we can use our relationship between power, voltage, and resistance. Power is still the voltage squared over resistance. The voltage here is 7 volts. We'll square that. The resistance is 6 ohms. 7 squared is 49 over 6. Let's reveal the answer. Save us the computation. 8.16 watts. So again, these are some examples of problems that you'll solve in your problem solving pack for homework or independently. I'm going to go ahead and paste the equations again for our use. What is the power consumption of a flash that draws 0.28 amps of current when connected to a 6-volt battery? So again, current's flowing, there's potential difference, so current's going to flow, energy is going to be consumed. In the case of the flash, we're converting electrical energy into light. So we're given I and V. So the equation that we can apply, I'll just circle it, is power is I times V. So power is current times voltage. That current is 0.28 amps times 6 volts. So it's roughly 1/4 of 6. Let's reveal the answer. About 1.5, actually 1.68 watts. 1.68 joules of energy are being converted every second. So again, a similar problem. There's problems always repeat themselves to show you multiple examples. Again, power is I times V. So you're given 0.33 amps of current. That's the I value times, whoops, let's fix that, times 100 volts. And 1/3 of 100 is, or are, 33 watts. In that ballpark. Very good. Keep the ball rolling here. A toaster consumes 560 watts of power. How much current is flowing through the toaster? So again, a toaster has filaments within it that offer resistance. When you run electricity through them, they convert energy to heat and a little bit of light, primarily heat, and we toast our toast. So let's go ahead and define the equations, throw them out there for review. In this problem, you're given resistance and you're given power, and the question is, what is the current? So we'll use the relationship between power, current, and resistance to solve for current. Power is I squared times R. Now this is going to require some manipulation in solving for I. I'll rewrite. Power is I squared times R. We'll divide by R. Cancel. And then I will be equal to the square root of power over resistance. We'll sub the numbers in. The power is 560 joules every second, or watts, whichever you prefer, divided by 30 ohms. So when we take the square root of 560 over 30, you end up with about 4.32 amps. What do 4.32 amps mean? That means 4.32 coulombs of charge travel through a point in that filament every second. Again, just a variation on problem solving. This is a different model toaster. It has 200 watts of power, and it sends current, or sends charges through a 50 ohm resistor filament. Again, power is I squared R. I will be the square root of power over resistance. The power is 200 watts. The resistance is 50 ohms. 200 divided by 50 is 4. Square root of 4 will give you 2 amps. Very nice. And we'll keep going. We're going to solve some more problems. Again, you're given a voltage of 30, a power of 600 watts. What is the magnitude of the resistance? Define the equations. So we want to solve for resistance. Let's go shopping for an equation. Power is I times V. We can't use that because we're given, we have to solve for resistance. Power is I squared times R. We're not going to use that because we are not given a current. Power is V squared over R. Do we know the power? Yes. We know P. Do we know voltage? Yes. Solving for R. So we use the last equation. Power is V squared over R. Solving this for R. R is V squared divided by P. Subbing in 30 volts squared divided by 600 watts. 30 squared will be 900 divided by 600 will give us 1.5 ohms. And again, we'll solve the same problem. It's going to be the same equation, so I'll rewrite. Power is V squared over R. R will be V squared over P. Solving, the voltage is 100 volts squared divided by 200 watts. 100 squared, 100 times 100 divided by 200 will give us 50 ohms of resistance. Alright, take some time to go through and problem solve on your own with the power problems, and you can refer to these videos if you encounter any difficulty, or you can work with a friend. Nice job. Alright, we're back. The next portion of the study deals with charge moving through a conductor. Charge moving through a conductor is a lot like water going through a pipe. And when we talk about the flow of charge, or when dealing with the flow of charge, dealing with the size of the pipe can determine how much water flows. So water can take many paths in this case, and how much water follows, I don't know, each path will depend on the path itself. This is an interesting picture. So the question is, how could the wire in the circuit affect the current? Wires offer resistance, and we'll define this a little bit early. The resistance of a wire depends on what type of material the wire is made of. That's called its resistivity. We use a Greek letter rho. Depends on the length of the wire. And then finally, the cross-sectional area of the wire. Talk about this in a second. If a wire is like a pipe, current is like water that flows through the pipe. So we can see here these waters would be currents. If there were pipes with water in them, what could we do to the pipes to change the speed of the water or the current? So if we wanted to decrease, let's just say decrease the resistance, make water go faster, we could decrease the resistivity, decrease the length, and increase the area. Excuse me. Let's take a peek at the answer. How about that? We could change the cross-sectional area to make it bigger. A larger cross-sectional area will give you smaller resistance. Change the length, and we wouldn't be changing the pipe itself, but we could change the resistivity. And the easiest way to remember this, wires like it, so wires with short resistances like it short. That means a small length. And the second thing they do, a big cross-sectional area. They like it fat. And then a sidebar thing, wires also like it cold. But we don't account for temperature in this formula. So we'll use this formula. I'm going to highlight it. So let's just highlight everything. I'll group this so we can refer to it, or paste it as needed. And copied in memory. So let's carry it forward. So the resistivity and resistance can be related. Resistance is the opposition to the flow of charge, and the resistivity is an intensive physical property that determines the resistance. So let's paste it. How are resistivity, which is rho, and resistance related? If you increase the resistivity, you would increase the resistance. The opposite of resistivity is conductivity. So again, we can see that resistance is proportional to resistivity, length, and inversely proportional to area. So every conductor conducts electric charge to a greater or lesser extent. Even insulators have some conductive property. Even insulators, or what we believe to be insulators, can move charge. Think about air. Air's excuse me, air is an insulator, but charge can move through it with lightning given a large enough potential difference or a large enough voltage. The last example also applies to conductors like copper wire. If we decrease the length or increase the cross-sectional area, we would increase the conductivity, thus decreasing the resistivity. So increased conductivity is the same as decreasing resistivity. Let's switch colors. Also, the measure of the conductor's resistance to conduct is called resistivity. Each material has a different resistivity. Again, it's represented with the letter rho. Combining what we know, area, length, and resistivity, we can find the total resistance. And again, just to show you, this is the equation we defined. So we'll carry that forward and use it. Resistance is measured in ohms. Cross-sectional area is measured in meters squared. Length is measured in meters, and resistivity is measured in ohmmeters. So how do we define the cross-sectional area for a wire? If I were to draw a wire, so just imagine a cylinder, the cross-sectional area is that face, and the area of any circle is pi times r squared. What is the resistance of a good conductor? A good conductor has a low resistance, and that means charge can move through it. So copper, it has a relatively low resistance. The electrons within this, if I draw, just imagine we have an electron, and we have an atom, an atom, an atom, so we're making all these little tiny lines of atoms. This electron is free to jump from one atom to another. Those electrons are said to be delocalized. So these valence electrons within copper are able to move from one atom to another, or electrons in general. This is a chart that gives us resistivity of some common conductors. We're always going to deal with copper for all the problems, so the resistivity is 1.68, but not 1.68 alone. 1.68 times 10 to the negative 8. That's a number we'll commit to memory, at least for this problem solving set, because we're going to always deal with the resistivity of copper. If we go in this direction, from the top to the bottom of the chart, the resistivity goes up. As we increase the resistivity, we'd be increasing the resistance. Now silver has a slightly smaller resistivity than, say, copper. Why not just equip our entire homes and electrical grid with silver conductors? It's not practical because silver is much more expensive than, let's say, copper, and so on. So in this problem, we're going to rank the materials in order from best conductor to worst conductor. And if you look, we deal with iron, copper, and platinum. Platinum, iron, and copper. Copper, iron, platinum. So we're going to deal with these: copper, iron, and platinum. So we'll draw dots next to these just to keep track. As we go from the top to the bottom, we increase resistivity, and if we increase resistivity, we would be decreasing conductivity. Conductivity is represented with another Greek symbol, so we'll go in this direction. So we go from copper to iron to platinum. As we go from copper to iron to platinum, we're going to increase resistivity. So copper has the smallest resistance, iron has a moderate resistance, platinum has a high resistance, so the worst conductor has the highest resistance. And the answer, according to our data table and our conclusions, will be C. So copper has, again, let's just draw, has a low resistivity, and platinum, well, we'll just steal this, has a high resistivity. What is the resistance of a 2-meter long copper wire whose cross-sectional area is 0.22 millimeters squared? So we're given a problem to solve for resistance. So we'll pull our friend out of our hat, our equation, and we're going to solve this for resistance. It's already been manipulated, so actually I'll just paste it again, and we can solve by subbing in numbers. Let's do this together. What is the resistance of copper? It depends on the resistivity of copper. If we go, how do we find the resistivity? Oh, it's not in the problem. Where do we find that resistivity, or resistivities in general? This information is tabulated in this data table. and copper has a resistivity of 1.688 times 10 to the negative 8 ohm meters. So that is 1.68 times 10 to the negative 8 ohm meters. So that's the rho value. The length up here is 2 meters. And then finally we're going to deal with a cross-sectional area, and we'll need to convert from millimeter squared to meter squared. So a common mistake is that folks will forget to make this conversion. And if I'm not mistaken, 0.2 millimeter squared will be 0.2 times. So the question is, how many square millimeters are there in a square meter? So if we had a square meter, not drawn to scale, there would be 10 to the 3, 1,000 millimeters in one direction and 1,000 millimeters in another. So that would give us 10 to the 6 millimeter squared per meter. So that's a fraction of it. So if I'm not mistaken, it's going to be 0.2 times 10 to the negative 6 square meters. Let's reveal our answer just to double check. That's right. If we look, we can cheat. We'll use the answer. Resistivity is 1.68 times 10 to the negative 8. The length is 2 meters. The area will be 0.2 times 10 to the negative 6 square meters, which gives us, and it's not converted in the first portion, and then it is converted to meters squared. It gives us 0.168 ohms, and we can just double check our units. Meters times meters. Try it again. Meters times meters will give us meters squared, divided by meters squared gives us ohms, and we are good to go. The next problem, there's an aluminum wire with a cross-sectional length of 900 meters and a cross-sectional area of 10 millimeters squared. So that is 10 times 10 to the negative 6 square meters. So we're going to convert that, and we'll go back and redefine the equation. So the question is, what is the resistivity? In this problem, we'll solve for rho, and rho will be R, resistance, times A, area, divided by length. The resistance in this case is 2.5 ohms as defined in the problem. The area is 10 times 10 to the negative 6 square meters, and the length will be 900 meters. Let's get rid of some units, and we end up with ohm meters, which are the units for resistance. Rather than doing the math, we'll solve for the resistivity for aluminum. Double check our answers. 2.5 ohms times 10 millimeters squared divided by 900. So we have 2.5 times 10 times 10 to the negative 6 is 10 to the negative 5 divided by 900 will give us 2.78 times 10 to the negative 8 ohm meters. Let's take a little trip backwards, and we'll see if that answer is what falls on the data table. Hopefully it is. For aluminum, 2.78. Remember that. What? That aluminum must not be pure. It must be an alloy, because we got a slightly different answer when we problem solved. Not the end of the world. What is the diameter of a 100 meter long copper wire that's found to have a resistance of 0.1 ohms? This is a tricky problem, so we'll walk our way through this. We're given the fact that resistance is rho L over A, so we need to figure out what the diameter is. If I draw a picture of a wire, and that's the area, we know that that area has a radius, and we know the radius is the diameter divided by 2, and the diameter will be 2 times the radius. So let's manipulate this equation and solve it for A first. A is rho L over R. So we could solve for that area, and once we know the area, we could find the radius, and once we know the radius, we could find the diameter. But we could solve this quickly by subbing in quite a few things. We know that area is pi r squared, and that will equal rho L over R. Pi r squared, what is R? R is d divided by 2, as stated here. What is r squared? If I square one side, I just square the other. So we get d squared over 4. So r squared, let's just stick with capitals to be consistent. R squared is d squared over 2. So we get pi times what r squared is, d squared divided by 4 is rho L over R. So now we solve for d squared. When we do this, d squared will be 4 rho L divided by pi r. There's a lot of algebra here, but nothing impossible, especially if we do it together. And to solve for this, we'll simply take the square root of both sides, and we're home free. So that's kind of messy. I'm going to erase to give us a little, no, I'm not going to erase, I take that back. We're just going to slide down. We'll end up with a little more room. I'm going to move this down so we can refer to it as we problem solve, and we'll solve for the diameter. I'll rewrite one more time. Diameter is the square root of 4 times the resistivity divided by the length divided by pi times r, which happens to be the square root of 4 times the resistivity of copper wire. Think back, we have to remember that. That is still 1.68 times 10 to the negative 8. Skipping units for just a moment, times the length, 10 to the 2 meters, that's 100, divided by pi, that's 3.14, sorry about that, times the resistance, 10 to the negative 1 ohms. So this is ohm meters. Let's just write units. Ohm meters times meters divided by ohms. What are ohms divided by ohms? That's 1. What are meters times meters? It's meters squared. Square root of meter squared will be meters. And then this is just a lot of computation. So let's just reveal the answer rather than pulling out the calculator and compare the substitution of the numbers in. So again, we have 4, that works. The resistivity of copper, we're good there. 10 to the 2 is 100 meters. Pi, 3.14. 10 to the negative 1 is 0.1. So we end up with 4.625 millimeters. Really, we're going to get an answer in meters and then convert to millimeters. Give this a shot yourself and see if you can compute that. That was intensive because it required a couple things. Number one, we had to start off with the equation for resistance, solve it for area. Once we solve for area, sub in pi r squared. Figure out what the diameter is in terms of the radius. Plug that in. and then sub everything in. So when you solve problems like this, you have to have a systematic, calculated approach. Show as much work as possible to keep track of everything, and then wait until the end before you sub in values, and you'll be home free. So again, give this problem a shot. When you're working through difficult problems, find a friend, and often together you'll achieve more. What is the cross-sectional area of copper wire whose length is some length L? Again, what we'll do is to paste the equation. Oh, there's our friend, still there, and we can solve this for A. And the area using this equation is the resistivity times the length divided by the resistance. Still dealing with our friend copper, happy and shiny. 1.68 times 10 to the negative 8 ohm meters times the length. Woo, that's a long spool of copper, 10K, 6 miles. So we'll deal with 10K, 10 times 10 to the 3. Let's just call it 10 to the 4 meters. Nice little run of copper wire divided by the resistance, 10 ohms. What is 10 in scientific notation? That's 10 to the 1 ohms. Yeah. So we'll do some cancellation. Area will be meters squared. When we put ohms over ohms, we'll be left with meters times meters. We get meters squared. So it works out dimensionally. Let's see if we can do this together. Old school. Go purple. What is 10 to the 4 divided by 10 to the 1? Subtract powers when dividing. That will simplify and give us 10 to the 3. What is 10 to the 3 times 10 to the negative 8? Add powers. I'll cancel my friends and rewrite. That will give us, running out of room, 10 to the negative 5. So we end up with canceling all the powers, and it leaves us with 10 to the negative 5. And then that area is 1.68 times 10 to the negative 5. Meters times meters will be meters squared. Who needs a calculator when we have our scientific notation? Makes things easy. So there's the answer. It works out. I love it when a plan comes together. Let's keep going. What is the length of 10 ohms of copper wire whose diameter is 3.22 millimeters? Ruh-roh. So we have one of these diameter problems. Let's give this a shot. Let's define what diameter is. Diameter is still 2 times the radius. So what is the length? Let's find our friend. See if our equation's still in memory. There it is. That's great. So what is the length? Let's manipulate this for length first. Length will be, let's do some algebra here. R times the reciprocal of this, A over rho. So we'll sub in now. Length will be resistance times area. That's pi r squared. Got to be careful. Resistance is r and radius is r squared. So let's do one thing just so we keep things clear. We will use a lowercase r for radius in this problem. I'll come up and rewrite. We don't want to have 2 capital R's. That will become very confusing. At least to me it is. Divided by the resistivity. So now we're good. Let's give it a shot. Length is r times r, and area is pi r squared divided by the resistivity. So now we're going to solve this in terms of diameter. What is r? R is diameter divided by 2, and r squared is still d squared divided by 2 squared. Oh, that's messy. Divided by 2 squared is 4 still. So I'll rewrite length is resistance times pi. What is r squared? That's d squared divided by the whole shebang, divided by 4. And we still have that resistivity in the denominator. So what is resistance? That's 10 ohms times pi times the length, or equals the length. What is the diameter? 3.2 millimeters. 3.2 millimeters are 3.2 times 10 to the negative 3 millimeters. So we have to be careful here. That's the diameter in meters. So we'll write that 3.2 times 10 to the negative 3 meters quantity squared divided by the resistivity, 1.68 times 10 to the negative 8 ohm meters times 4. So this is a problem where, you know, you're going to get an answer. Let's take a peek at what the answer is. A long distance in meters, about 5,000 meters, 4,787.2 meters. So let's see if we can approximate this. Sometimes I'll cheat and approximate answers without using a calculator. 10 ohms, or let's do the units first. We have ohms over ohms, that cancels. Pi is a constant, it does not carry units. So we have meters squared divided by meters. That will give us meters. So the units will work out. So we're good to go there. Let's approximate. What pi is 3.14. Sometimes in my world I'll just call that 3. What is 3 times 10? That's 30. So we're accounting for the 10 and the pi. Next we're going to square everything inside of the parentheses. What is 3.2? That's almost 3. So what is 3 squared? That's 9. What is 10 to the negative 3 squared? That's 10 to the negative 6. Divided by 1.68. I'm just going to call that 2. Times 10 to the negative 8. I just round everything. Divided by 4. What is 2 times 4? I'm going to call that 8. What is 9 divided by 8? Oh, let's just call that almost 1. So that will leave us with, let's just highlight what's left. We're left with the 30. We're left with the 10 to the negative 6 and the 10 to the negative 8. We're going to be off by quite a bit in this approximation, but we'll round it to the nearest order of magnitude. That's how I'll bail myself out. So what is 30? We'll just write that out there. That will be 30. And then what is 10 to the negative 6 divided by 10 to the negative 8? So when you do that, it's 10 to the negative 6 minus negative 8. That's negative 6 plus 8. That's 10 to the 2. What is 30 times 10 to the 2? That will be 3 times 10 to the 3. So I got an answer that's approximately 3,000 meters, because I'm approximated quite a bit. I've made quite a few assumptions, which errors propagate continuously. But really, what's the best answer? 10 to the 3 meters. If I approximate this to the nearest order of magnitude, and you'll be a lot more precise, you'll get an answer closer to 4,787.2 meters when you use a computer. But I found that my answer 3,000 is close enough to 5,000 because this is also of an order of magnitude 10 to the 3 meters. Okay, we realize that I'm off by a little bit, but we'll deal with it. Again, big picture here. Use a systematic approach. Ooh, that's a lot of problem solving. Use a systematic approach to problem solving. Write what you know as a starting point. Manipulate. Again, if you don't have a variable to solve for, you use the system of equations. Write what the diameter is in terms of the radius, and then sub it in, solve for the unknown based on what you're given. Do the conversions. Approximate if you have to, especially if you don't have a calculator, and you'll be home free. A lot of work on that problem. Let's stop this video for now before we go on.